はい、始めます。今ツイートしたこれですね。アシュクロフト・マーミンの、ソリッド・ステート・フィジックスを始めたいと思います。で、ブルーキャットにあるのはこういう感じです。第3回で第1章パート3です。テキストブックがここにある。これあとハッシュタグ入れてないな。ハッシュタグは後で入れときます。後で入れとこう。それで、このアシュクロフト・マーミンのソリッド・ステート・フィジックス、有名な教科書の今日は、3ページからやります。それで、どこだテキストはここにあると。コンパスの方も今日の3月8日2時から始めるということで、第1章パート3で、こうなってます。はい、いいです。で、テキストはこのギガファイルにありますので、こうクリックすればダウンロードできます。それで3ページからいきます。どこだ3ページ。この辺からでいいのかな。Although there is only one kind of particle present in the simplest gases, in a metal there must be at least two. For the electrons are negatively charged, yet the metal is electrically neutral. Drude assumed that the compensating positive charge was attached to much heavier particles. Positive charge was attached to much heavier particles, which he considered to be immobile. At his time, however, who is he? Drude. At his time, however, there was no precise notion of the origin of the light mobile electrons and the heavier immobile positively charged particles. The solution to this problem is one of the fundamental achievements of the modern quantum theory of solids. Solution to this problem is one of the fundamental achievements of the modern quantum theory of solids. In this discussion of the Drude model, however, we shall simply assume, and in many metals this assumption can be justified, simply assume that when atoms of a metallic element are brought together to form a metal, the valence electrons become detached and wander freely through the metal, while the metallic ions remain intact and play the role of the immobile positive particle. In Drude theory, so intact in Japanese is difficult. 無償as it is. Play the role of immobile immobile positive particle in the group theory. This model is indicated schematically in figure 1.1. This is figure 1.1. Schematic picture of isolated atom, not to scale. In a metal, the nucleus and ion core retain their configuration in the free atom. In a metal, the nucleus and ion core retain their configuration in the free atom, but the valence electrons leave the atom to form the electron gas. Valence electrons leave the atom to form the electron gas. Nucleus, core electrons, valence electrons. In solid, conduction electrons. Ion consists of nucleus and core. Okay. A single isolated atom of the metallic element has a nucleus of charge EZA, where ZA is the atomic number and E is the magnitude of the electronic charge. We shall always take E to be a positive number. E equal 4.8 times 10 to the minus 10 electrostatic units. ESU equal 1.60 times 10 to minus 19 coulombs. Surrounding the nucleus are Ga electrons of total charge minus EZA. A few of these Z are the relatively weakly bound valence electrons. The remaining Za minus Z electrons are relatively tightly bound to the nucleus. Remaining Za minus Z electrons are relatively tightly bound to nucleus, play much less of a role in chemical reaction, and are known as the core electrons. When these isolated atoms condense to form a metal, the core electrons remain bound to the nucleus to form the metallic ion, but the valence electrons are allowed to wander far away from their parent atoms. In the metallic context, they are called conduction electrons. Footnote 4. When, as in the Drude model, the core electrons play a passive role and the ion act as an indivisible inert entity, indivisible inert entity, or one often refers to the conduction electrons simply as the electrons, saving the full term 4 times. When the distinction between conduction and core electron is be emphasized. When the core electron play a passive role at the ion act as indivisible inert entity, one often refers to the conducting electron simply as the electron, saving a full term for times when the distinction between conduction and core electrons is to be emphasized. Drude applied kinetic theory to discuss of conduction electrons of mass m, which, in contrast to the molecules of an ordinary gas, move against a background of heavy immobile ions. The density of the electron gas can be calculated as follows. Metallic element contains 0.6022 times 10 to 24 atoms per mole, Avogadro number, and rho m divided by A moles per cubic centimeter, where rho m is the mass density in grams per cubic centimeter and A is the atomic mass of the element. Since each atom contributes Z electrons, the number of electrons per cubic centimeter n equal large N divided by V is small n equal 0.6022 times 10 to 24 times 0 m divided by A. Table 1 shows the conduction electron densities for some selected metals. They are typically of order 10 to 22 conduction electrons per cubic centimeter, varying from 0.91 times 10 to 22 for cesium up to 24.7 times 10 to 22 for beryllium. Also listed in table 1.1 is a widely used measure of the electronic density, RS, defined as the radius of a sphere whose volume is equal to the volume per conduction electron. Thus, V over N equal 1 over small n equal 4 pi RS cube to the power 3 divided by 3. RS equal 3 over 4 pi n to the power 1/3. Footnote 5. This is a range for metallic elements under normal conditions. Higher densities can be attained, by application of pressure, which tends to favor the metallic states. Lower densities are found in compounds. Table 1.1 lists RS both in angstroms, which is 10 to power minus 8 centimeter, and in units of Bohr radius. A0 equal h bar square divided by me square, which is 0.529 times 10 to minus 8 centimeter, the latter length being a measure of the radius of a hydrogen atom in its ground state, is often used as a scale for measuring atomic distances. Note that RS divided by A0 is between 2 and 3 in most cases, although it ranges between 3 and 6 in alkali metals and can be as large as 10 in some metallic compounds. Metallic compounds. 2 and 3 in most cases, although it ranges between 3 and 6 in alkali metals and can be as large as 10 in some metallic compounds. These densities are typically 1,000 times greater than those of a classical gas. Densities are typically 1,000 times greater than those of a classical gas at normal temperatures and pressures. In spite of this, and in spite of the strong electron and electron-ion electromagnetic interactions, the Drude model boldly treats the dense metallic electron gas by the method gas by the methods of kinetic theory of a neutral dilute gas with only slight modifications. The basic assumptions are these. Number 1. Between collisions, the interaction of a given electron both with the others and with the ions is neglected. Between collisions, the interaction of a given electron both with the others and with the ions is neglected. Thus, in the absence of externally applied electromagnetic fields, each electron is taken to move uniformly in a straight line. In the presence of externally applied field, each electron is taken to move as determined by Newton's law of motion in the presence of those external fields, but neglecting the additional complicated field produced. As complicated field produced by the other electrons and ions. Footnote 6. Strictly speaking, the electron-ion interaction is not entirely ignored. For the Drude model, implicitly assumes that the electrons are confined to the interior of the metal. Evidently, this confinement is brought about by their attraction to the positively charged ions. Gross effects of the electron-ion and electron-electron interaction like this are often taken into account by adding to the external fields a suitably defined internal field representing the average effect of the electron-electron and electron-ion interactions. Complicated. Gross effect of the electron-ion and electron-electron interaction like this are often taken into account by adding to the external field a suitably defined internal field representing the average effect of the electron-electron and electron-ion interaction. The neglect of electron-electron interactions between collisions is known as the independent electron approximation. The neglect of electron-electron interactions between the collisions is known as the independent electron approximation. The corresponding neglect of electron-ion interactions is known as the free electron approximation. We shall find in subsequent chapters that although the independent electron approximation is in many contexts surprisingly good, the free electron approximation must be abandoned if one is to arrive at even a qualitative understanding of much of metallic behavior. Free electron approximation must be Independent electron approximation is in many contexts surprisingly good. The free electron approximation must be abandoned if one is to arrive at even a qualitative understanding of much of metallic behavior. Okay, so this is the table 1.1, free electron densities of selected metal elements. Lithium, G is 1. That means this is alkali metal. Alkali metal. RS. Let's see. Beryllium. This is the smallest. I think beryllium. This is the smallest. This is the largest. 2.9. This is the largest. Cesium. Beryllium, cesium. gallium, indium. I don't know why I have a line here. So this is almost, RS is almost 1. RS divided by A0 is between 2 and 3. So that means RS is something like 1 to 1.5 angstrom. Iron 1.12, manganese, alpha manganese 1.13, zinc 1.22, cadmium 1.37, mercury 1.4, aluminum 1.1, gallium 1.16, indium 1.27, thallium 1.31, tin 1.17, lead 1.22, bismuth 1.19, antimony 1.13, barium, strontium, niobium, calcium, magnesium, beryllium. Oh, beryllium is very small. Magnesium, alkali metal. How do you call this? Valence electron 2. Alkali. I forgot. Okay, so a room temperature above 300 Kelvin and atmospheric pressure, I don't know where is the accent. Atmospheric pressure, unless otherwise noted, the radius Rs of the free electron sphere is defined in equation 1.2. We have arbitrarily selected one value of Z for those elements that display more than one chemical valence. The Drude model gives no theoretical basis for the choice. The Drude model gives no theoretical basis for the choice. Values of n are based on data from R.W.G. Wyckoff, Crystal Structures, 2nd edition, Interscience, New York, 1963. Value of n. Anyway, so we go to number 2. Number 2, collisions in the Drude model, as in kinetic theory, are instantaneous events that abruptly alter the velocity of an electron. Drude attributed them to the electrons bouncing off the impenetrable ion cores. Rather than to electron-electron collisions, the analog of the predominant collision mechanism in an ordinary gas. Okay. I think this one. Them means collisions. Drude attributed collisions to the electrons bouncing off impenetrable ion cores. Rather than electron-electron collisions, the analog of the predominant collision mechanism in an ordinary gas. We shall find later that electron-electron scattering is indeed one of the least important of the several scattering mechanisms in the metal. Indeed, we shall find later that electron-electron scattering is indeed one of the least important of the several scattering mechanisms in a metal, except under unusual conditions. Under some unusual conditions, electron scattering is important. However, the simple mechanical pictures, figure 1.2, of a electron bumping along from ion to ion is very far off the mark. For some time, people were led into difficult but irrelevant problems connected with the proper aiming of an electron at an ion in each collision. So literal an interpretation of figure 1.2 is strenuously to be avoided. For some time, people were led into difficult but irrelevant problems connected with the proper aiming of an electron at an ion in each collision. I don't understand. For some time, people are led into difficult but irrelevant problems connected with the proper aiming of an electron at an ion in each collision. So, literal an interpretation of figure 1.2 is strenuously to be avoided. For some time, people were led into difficult but irrelevant problems connected with the proper aiming of an electron at an ion in each collision. So literal an interpretation of figure 1.2 is, let me see, let me try deep well. So literal an interpretation of figure 1 is strenuously avoided. Okay. So let's see 1.2, figure 1.2, trajectory of a conduction electron scattering off the ions according to the naive picture of Drude. Where are we now? Here. Simple mechanical picture of an electron bumping along from one ion to bumping along from ion to ion is very far off the mark. However, fortunately, this does not matter for many purposes, A qualitative and often a quantitative understanding of metallic conduction can be achieved by simply assuming that there is some scattering mechanism without inquiring too closely into just what that mechanism might be. By appealing in our analysis to only a few general effects of the collision process, by appealing to only a few general effects of the collision process, we can avoid committing ourselves to any specific picture of how electron scattering actually takes place. These broad features are described in the following two assumptions. These broad features are described in the following two assumptions. Okay, number 3. We shall assume that an electron experiences a collision. I.E. suffers an abrupt change in its velocity with a probability per unit time 1 over tau. We mean by this that the probability of an electron undergoing a collision in any infinitesimal time interval of length dt is just dt over tau. The time tau is variously known Oh, sorry. Just a minute. It doesn't work. Okay. Variously known as the relaxation time, the collision time, the mean free time, and it plays a fundamental role in the theory of metallic conduction. It follows from this assumption that an electron picked at random at a given moment will, on the average, travel for a time tau before its next collision. And will, on average, have been traveling for a time tau since its last collision. Footnote 8. See problem 1. Okay. In the simplest assumption applications of the Drude model, the collision time tau is taken to be independent of an electron's position and velocity. We shall see later that this turns out to be surprising good assumption for many, but by no means all, applications. Number 4. Electrons are assumed to achieve thermal equilibrium with their surroundings only through collisions. These collisions are assumed to maintain local thermodynamic equilibrium in a particularly simple way. Immediately after each collision, an electron is taken to emerge with a velocity that is not related to its velocity just before the collision, but randomly directed and with a speed appropriate to the temperature prevailing at the place where the collision occurred. Thus, the hotter the region in which a collision occurs, the faster a typical electron will emerge from the collision. Number 9. Given the free and independent electron approximation, this is the only possible mechanism. Left. Electrons are assumed to achieve thermal equilibrium with their surroundings only through collision. Given the free and independent electron approximation, this is the only possible mechanism left. Given the free and independent electron approximation, this is the only possible mechanism left. I think this is something like this. In order to achieve thermal equilibrium, necessary. Necessary mechanism. This is the only necessary mechanism. In the rest of this chapter, we shall illustrate these notions through their most important applications, noting the extent to which they succeed or fail to describe the observed phenomena. Okay, so I can stop here, and it's page 6. Next time, page 6, electric